Hello and welcome. Welcome to the C3 AI DTI seminar series. So my name is Richard Zhang. I am an assistant professor here at the University of Illinois. I am co-hosting this seminars series with Gary Joshi, who is an associate professor at CMU. So the C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthroughs with large-scale societal benefits. Before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we are deeply grateful. So our fall 2022 series is organized around two special themes: adversarial machine learning and distributed and federated learning. Our talks are scheduled to alternate between these two themes over alternating weeks. We have some really exciting speakers lined up for the semester. Just to give you an idea, for the next 4 weeks, we'll be hearing from Brendan McMahon from Google, Zico Coulter from CMU, Eric Zhang also from CMU, and Tom Goldstein from the University of Maryland. And our series will extend all the way out to December with speakers featured here. And you can find the details of the speaker information and abstracts on our website. So you can find abstracts for future talks at the website as well. The videos of previous talks, both from the current semester as well as the past series, will also be available on our YouTube channel. And we invite you to subscribe to our newsletters and our channel so that you don't miss these talks. So today we are very happy to welcome Professor Lee to share her research with her talk entitled Trustworthy, Machine Learning, Robustness, Privacy, Generalization, and the Interconnections. Professor Lee is an assistant professor in the Department of Computer Science at the University of Illinois. She is the recipient of many prizes, including the IJCAI Computers and Thought Award, Alfred P. Sloan Research Fellowship, the NSF Career Award, MIT Technology Review TR 35 Award, Dean's Award for Excellence in Research, the CW Gear Outstanding Junior Faculty Award, the Intel Rising Star Award, Symantec Research Labs Fellowship, and research awards from tech companies including Amazon, Facebook, Intel, and IBM, and Best Paper Awards at several top machine learning and security conferences. So her work has been featured by major press outlets including Nature, Wired, Fortune, and the New York Times. And without further ado, I'd like to welcome Professor Lee. So to give you an idea, the talk will be 50 minutes. For the audience, please use the Q&A feature down below to submit your questions, and we'll ask the questions on your behalf at the end of the talk. So whenever you're ready, Professor Lee.
Okay. Thank you, Richard, for the nice introduction. And it's really a great honor for me today to share our research about trustworthy machine learning here. So given this is a big area, so today I will mainly talk about the one types of unified view of trustworthy machine learning itself regarding the robustness, privacy, generalization, and underlying interconnection, and what's the principles behind it, and then dig into one types of interesting topic about using domain knowledge and reasoning ability to improve the certified robustness of machine learning models. So yeah, let's jump right in. So first of all, I don't think I need to mention a lot that machine learning currently has been ubiquitous, and it's, for example, autonomous driving, intelligent medical treatment, and many other security critical applications like malware classification. And keep in mind that later on in the talk, I will mainly use autonomous driving and a small example of malware classification as an example to go through to see how we can improve the robustness against such applications, which is quite safety critical, but of course it can be applied to many other domains as well. So given such very powerful machine learning and AI techniques currently, right, we have seen so far a lot of severe security and privacy concerns in real world already. Here I want to give some quick examples for those who may not realize how vulnerable our machine learning models currently is. For example, in 2016, the White House Associated Press Twitter account was hacked in phishing emails, spreading the rumor that the White House has been attacked, which actually as very easy to detect fake news, but even, I mean, for human, but for machine learning models like the autonomous trading bot, actually they are fooled and triggered it to dump a large amount of stocks within seconds and swap about $136 billion within seconds, which is a real threat in real world. And similarly, from the privacy perspective, there are different biometric recognition systems deployed for safety screening, for like personalization, et cetera, which raise a lot of privacy concerns. As you can see, a lot of sensitive information are stored in certain database or even in cloud. Therefore, we can see, even though I would say we are very lucky to live in this nice world with a lot of convenient platforms and tools to help us develop different machine learning algorithms and pipelines to play with our data and try out different analytics. But still, we have to realize that we are living in an adversarial environment. So a typical machine learner still have a very hard life so far to develop the so-called trustworthy machine learning pipelines. And therefore, I think that's why we need to be aware of this and understand different threat models, strategies, capabilities of attackers, and hopefully can develop different types of certified or trustworthy machine learning pipelines, right? But before we go to like details about the things, and on the high level, we can see that just regarding trustworthiness itself, it has a lot of different perspectives, right? Including robustness, privacy, as we just seen, and also fairness, expandability, et cetera, and generalization, right? So with so many like perspectives, and what's, if we get a chance to ask, what's one fundamental question behind it, and what's one like a problem that we aim to solve under this big umbrella area, I would say that from my point of view, that we are doing all the work trying to hope to close this trustworthiness gap between different distributions. And I would say this can be viewed as one unified view that is trying to, that is able to unify different perspectives of trustworthy machine learning topics under it. Concretely, as an example, we can see from the robustness perspective, right, which is like very well discussed recently, recent years, and we can see if, say, here the trustworthiness gap in robustness itself specifically means distribution between the training and testing, right? For example, if the training distribution is manipulated by the attacker, it will lead to the so-called poisoning attack, like a backdoor attack, et cetera, we have seen so far. And if on the other hand, the test time distribution have been attacked, it will lead to the evasion attack, testing time attack, and many the adversarial examples that you are familiar with, right? And under this framework, that's different, say, game theoretical modeling and different ways to certify the improvement, the robustness of the machine learning models is proposed and studied, aiming to close this distribution gap. And on the other hand, from the privacy perspective, indeed, we are also trying to close the gap between the distribution such that the attacker is trying to, say, by probing the model, can infer different individual private sensitive information. And from the defender perspective, we are trying to close this distribution deviation or shifting gap such that the individual sensitive information will not lead to the difference from the distribution level, such that the attacker cannot obtain useful sensitive information from it, right? From this point of view. And similarly, from generalization perspective, you can see or view it as a natural distribution shifting or an analysis compared with the worst case distribution gap analysis under the robustness perspective. Right. So not only about the individual pillars here, but also I would really want to emphasize here that there are underlying connections among different topics is also very important, because with such underlying principles understanding, it is possible that we don't need to reinvent the wheels to do one topic from the other, and we can identify their connections and we can leverage the methodology developed from one perspective to help the other. I think that will largely benefit this community. Give some very concrete example or quick example is that, for example, we have been able to prove that if, say, a federated learning model is satisfying the, say, epsilon delta differential privacy, we can actually represent the certified robustness of that model as a function of the epsilon delta here to build this connection, right? And similarly, we can prove the bidirectional indicator from the robustness and generalization. So intuitively, you can see that that's true, that if the model is very generalizable, it's generalized to arbitrary distribution, right? So it should generalize to adversarial worst case distribution. Therefore, they should have some connection, right? But importantly, if we can identify and prove their bidirectional indication, I think it's indeed very helpful for both areas. And similarly, from the privacy and generalization, they have a strong underlying connection as well. So I think this unified view could be very helpful in terms of us understanding the trustworthy machine learning area. And of course, there are other pillars I didn't mention here, like fairness or explainability, and we actually can prove the indication between the generalization and the fairness, and provide a certified bound for fairness itself, given certain models. But in this talk, based on this unified overview, unified view, I will mainly talk about the robustness itself, which is a very important topic, and mainly focus on how to leverage knowledge and reasoning ability to improve the certification of machine learning pipelines. And then I will touch a little bit about how we can connect these two. And for other topics, if you are interested, we can discuss as well. And in terms of robustness, here I will first use, say, 3 minutes to go through what vulnerabilities we have seen so far in real world, in case some of you haven't realized the severe vulnerability, I would say. And then we'll dig into the improvement of the certified robustness itself. So first of all, I think many of you may have seen such an example about the static row sign here. So basically we are able to optimize different stickers, say even just the white and blank rectangles or letters under different angles and reasoning conditions. And unfortunately, all the row signs, like stop signs here, can be misrecognized as speed limit sign 45, and the right-hand side will misrecognize the stop sign in the static evaluation. And again, in a dynamic evaluation, you can see such a row sign, even in physical world, when you actually drive a car towards it, it's also consistently misrecognized as a speed limit sign, but the control experiment can always recognize itself, right? And not only against such a classification model, but also against object detection model, right? Still, you cannot recognize this sign. Obviously, it's a stop sign to human, but a machine learning model, this is fast RCN here, cannot recognize it, even though all the other objects can be correctly recognized, right? And so far, we are talking about these types of called white box attacks, which means we have access to the models. But unfortunately, the black box attack, which is very realistic in physical world, is also possible in the sense that one types of black box attack is called based on adversarial transferability, meaning that even in this different environment, like if we use the same perturbation or like optimize the trigger here to attack the different model like YOLO here, it still can fool the model unless you go to very close to the sign itself, which is too late for a car to stop, right? And basically, this sign itself is actually possible in real world and also exhibited in the Science Museum London and raise a lot of social concerns. And so far, we talk about, say, the camera sensors, right? And in addition, it's possible actually to not only attack these types of planar object against cameras, but also against, say, the object of like a real 3D object like LiDAR sensors. For example, here, if we optimize the object and then 3D print it out and drive a car towards it, you can see from the LiDAR perspective, it never recognizes this object here, although it's clearly here. But in the control experiment, if we put a box of similar size here, you can see from the green box, the LiDAR can always detect this object, which you can see in real world if the car cannot detect a weird optimized adversarial object, it can risk severe consequences. And not only against the single sensors like cameras, LiDARs, and here, but also even against the complicated multi-sensor fusion systems, right? And here, I don't want to go to details about it, but just to show an interesting example that this is against the real simulation for LG and Apollo, and you can optimize an object, adversarial object, with both shape and texture, and simultaneously fool both the LiDAR and the camera sensors together, even though they have complicated aggregation protocols. For example, here in this simulation, the car will never recognize such a adversarial object and run into it, which in real world, it can be quite dangerous. But in the control experiment, you can see this object looks quite similar with the adversarial one, but the car actually can recognize it and stop at it. So there are many other examples on the website, and if you are interested, you can play with it. But then with all this, so far seeing these different types of attacks in real world, right? I hope it's convincing enough for you that indeed the real world machine learning and AI algorithms, although on some tasks, they have achieved even better performance than human, right? But they are indeed very vulnerable to different adversarial manipulations or attacks. So in order to improve the robustness of the machine learning models, right? So far, there are lots of defense or detection or prevention methods have been proposed. And this is just some examples, but there are a lot of others not here yet. But unfortunately, one bad news is that against all these empirical defenses or detection approaches, there are a lot of later work that have been proposed to adaptively attack them again successfully. And therefore, as we know that in security, we have this famous cat and mouse game. We have new attacks, we have new defenses, and maybe new attack come out later. So really, we hope to have a way to sort of end this game so that we can have certain guarantees of the robustness or safety of whatever model we can deploy in real world, so that we have some confidence about the vulnerability under even unforeseen adversarial attacks or manipulations, right? So as we can see, this goal itself is very important. And therefore, here we want to mention one specific types of robustness here, which is the certification. So basically, the high-level goal of the robustness certification itself is to provide some sort of lower bound of the machine model accuracy under certain constraint attacks. Slightly more concretely, you can see this simple optimization itself, which is from the defender's perspective, you hope to minimize the loss, give over the parameters that you can optimize against a worst case attacker, which the delta here is the perturbation. And then the transpose delta here means any adversarial transformations. You can be a simple additive noise, or you can be different semantic transformation, etc. And here, this distance function represents the constraints of the attack. It can be LP non-bounded, it can be certain semantic like a color or lightning constraint bounded, etc., etc. So eventually, we hope that under the worst case attackers, given some constraints of their capabilities, we can minimize the loss of the model such that we can get an upper bound estimation of this loss function, which is the lower bound of the accuracy itself, so that we know, okay, if the lower bound of the accuracy of the model is 90% under certain attacks, we know there is no further attack that can be conducted to lower down this accuracy as long as the attack satisfies certain constraints, right? So I think this goal itself is very nice. And in order to achieve this, so far there are many certification algorithms have been proposed. Essentially want to address or solve this min-max problem, because you can see, given a deep neural network, the model loss function itself is non-convex and very complicated. So we need different ways to solve such a min-max problem. remember this, that we will discuss, need to discuss this later on as well. So basically there are different ways, deterministic way and the probabilistic view, to solve this min-max and upper bound this loss or lower bound accuracy. And we can see under the deterministic verification, either we can have a complete verification by exactly solve this problem using exact solvers, but we can imagine this is very expensive, right? And therefore we can do some relaxation to provide some incomplete verification, meaning that this will provide both sufficient and necessary condition, and this will provide only sufficient condition, meaning if the certification method say this instance is certifiably robust against this model, then it will be indeed certifiably robust. But on the other hand, if it says that it's not certifiably robust, it could be either because of the model certification method is too loose that you cannot certify, or because of that the instance indeed is not certifiably robust. So there could be different reasons. So it only provides sufficient condition. And so far, only this probabilistic view can scale up to large scale data sets such as ImageNet, etc. And corresponding to different certification methods, there are different robust training methods also can be like used or leveraged to improve the corresponding certification to like improve the basically the lower bound here that get tighter and tighter. And we actually have maintained up-to-date leaderboard for all the certification method here and the robust training method here on the different conditions. And if you are interested, it may make your job easier to directly leverage the result and the implementation here. So far, we can see that this is very nice, and it provides rigorous and nice certification for the robustness of machine learning models. But on the other hand, it's also expensive, as we can see, right? And we need to solve this expensive optimization problem and loose in many cases, right? And how loose it is, let's take a quick example of the CIFAR. So basically, against the small, simple data set MNIST, under one types of constraints, say L infinity norm of the magnitude of privation, like this, the certified robustness so far is 93 and the empirical one is 96. So we would say that there is actually no big difference between these two gaps, which is great, right? However, if we go to slightly larger or slightly more complicated data sets, say on CIFAR, we can see so far under such a constraint, the certified robustness is only 40, but the empirical robustness is 66. It means either that our existing certification is too loose, we can improve this value, or we haven't found effective enough attacks yet to lower down this value to match the certification. So there's a relatively big gap here, right? And this gap, such a gap is interesting to lead to very promising new research about certification and attacks, etc. But unfortunately, if we leverage some on some scalable or more practical large-scale data set like ImageNet, right? So far, certification is only 30%, and there is a huge gap. And even for empirical robustness, it's also challenging to improve it. Therefore, based on such certification implementation, we do need to think about whether there's other ways to improve the robust certification of it, right? And particularly, we want to ask about the question that, as so far we can see, all the statistical models, which not highly, like fully rely on data itself, right? The data-driven types of statistical models. If the data itself is vulnerable, as we mentioned, that the distribution can be manipulated a little bit, such that the model will always be vulnerable, right? And it's almost reach certain bottleneck to improve the certification of the machine learning model itself, based on my personal opinion. So the question now we want to ask is, can we leverage additional information in addition to the data itself, right? For example, in all the examples we've seen before, like the road signs and the LiDARs, all the things, as human, we cannot be fooled, right? Maybe it's because human, we have knowledge, we have logical reasoning, we have experience, etc. But essentially, those are useful information that we hope that we can integrate to machine learning models to improve their robustness, right? And of course, we need a principled way to do that. And also we also hope to leverage the good expressiveness of current, say, deep neural networks or machine learning models. We do not want to go back to the original rule-based prediction, of course, right? So in order to achieve all these hypotheses or goals or assumptions, what can we do, right? So basically here, I want to mention one possibility, but I believe there are other possibilities as well. So which is here one example we proposed, and we'll dig into this about a sensing-reasoning pipeline. So basically what you have here is that you can leverage the sensing model, which can be realized by different, say, deep neural networks, takes the input, say, an image, and gives output. And now we will connect a reasoning component behind it rather than trust the output directly, which we know will be vulnerable, right? And the reasoning component can be realized by different probabilistic graphical models, for example, Markov logic nets, Bayesian nets, etc. And the output of the sensors will be taken as the input of such a reasoning component. And here there will be different knowledge rules to connect the relationship of the output of different sensors, right? For example, if this sensor shows it's a dog, this sensor predicts it's an animal, then we know the dog belongs to an animal, right? And the intuition here is that it should be hard for the attacker to attack all the sensors altogether and still preserve the logical relationship here, right? And as long as some or even one of the logical relationship is violated because one of the models is, say, attacked, then it's possible for the reasoning component to recorrect all the prediction probability here to get a correct final end-to-end prediction. And we'll look at the concrete example later. And here, as we can see, given such a pipeline, we still hope to get a certification of it, right? Basically, the certification here means that we want to get the upper lower bound of the maximal change of the marginal prediction probability of the final end-to-end prediction here, right? And the challenge, of course, is now we need to solve the min-max problem we mentioned before for this end-to-end pipeline, right? How we can actually solve that and get the certification. So concretely, given this pipeline, we have three questions to ask, right? The first is, as we mentioned, given such a reasoning component, although given the previous slides, we already see there are many work proposed to certify a single neural network robustness, right? So given such a complicated, say, Markov logic net, how can we certify the robustness of it, right? So first, we want to get a sense of it so that we can get end-to-end certification based on the connectivity here, right? And the second, we want to also answer that whether we can prove such a sensing reasoning is indeed more robust than a model without any knowledge integration, and under what types of sufficient conditions this is true, right? So that we know when and how we can use such a pipeline. And in the end, of course, that's most important problems or questions people may care about is how we make this sensing reasoning end-to-end pipeline scalable so that it can be scalable to real-world applications and data sets, etc., right? So we will quickly try to dig into each one and get some sense for the answer of each question. If you get answers already, keep it in mind and we can discuss whether you get a better solution, right? So here, let's look, to answer the first question, let's look at concrete realization of such a sensing reasoning pipeline. So basically here, again, give an input, say it's a dog, and we can build different sensors for it, like predict whether it's dog, it's cat, it's animal, etc. And all this will be viewed as a variable input as a reasoning component. Here is MLN as an example, and we'll have different factors here to connect them. For example, here is some rules like dog belongs to an animal and cat belongs to an animal and dog cannot swim, etc., etc., right? And we'll learn different ways for those factors. And here we have different types of factor. One is the interface, which directly connect with the sensors, and one is the interview, which connects the internal knowledge relationship here. And remember, the goal of us is to certify the robustness, basically the upper lower bound, the marginal prediction probability of such a MLM pipeline, right? And first, we need to know in this MLM program, what's the marginal prediction probability, right? So basically, it can be represented as a Z1 divided by Z2. Z1 here meaning all the assignment that satisfy the knowledge rule here, and Z2 means all the possible word of all the possible assignment. So this is the correct prediction. This is the prediction probability, right? And we can see we definitely want to upper lower bound this, and therefore based on the graph structure itself, a good thing is that we can represent Z1 and Z2 just as the graph itself based on the factors we have, the interface and interior factors we have here. And with this, we can first see how hard it is to certify this MLN, right? Very unfortunately, it is very hard. It is NP-complete. So basically, without digging into details, we can see that there's a famous counting problem. The format looks like this. Actually, if we want to certify the robustness of MLN itself, we can reduce the counting problem into the robustness problem. Therefore, we can write it in a similar format here, such that we can see the sigma here represents the benign distribution, and here is the adversary, and we want to bound their difference. And in order to get this difference, it's NP-complete, right? And therefore, now what do we do, right? So of course, we can do approximation, right? And the thing is how tight our approximation is. So concretely, and I think very interestingly, we show that it is possible to approximate the certification upper lower bound of MLN as long as given some oracle to the statistical inference of MLN itself. And concretely, what we can do is that, remember, we want to get the upper lower bound of Z1 divided by Z2, right? And if we take a log, what we want is just a log Z1 minus log Z2. Here, in terms of the mean and max, we just want to get the max minus mean and want to get the mean and max. So basically, this is very intuitive. And the main challenge, as we can see here, is we hope to get the max and the mean of this Z itself. And the Z itself is the inference of MLN, and it can be equal to the ground truth, which we don't know, plus some perturbation, and epsilon is a perturbation bounded by magnitude C here, lambda is certain coefficient we don't know in practice, right? So with such assumption, or the instead of assumption, I would say it's a development, right? Very interestingly, we can prove that it's such a probabilistic graphical model family have a nice property, which is that such a complicated Z delta can be either monotonic when the lambda coefficient itself is larger than 0 or smaller than -1, or it will be convex when the lambda is between -1 and 0. So as you can see, then it becomes easy to directly get the mean and max of this Z delta, right, based on such property. So yeah, for detailed proof, you can take a look at the paper. I think it's very interesting. But I think most importantly here, we have this signal that the mean and max of this Z delta under this constraint of attacks can be proved and analyzed. And in this way, it's possible that we can upper lower bound of it and get the certification. And give a concrete example here, we can see that this is a PrimateNet from ImageNet, and there are a lot of, say, primate classes, and we will only need to use 2 types of simple knowledge. For example, the hierarchy knowledge, meaning that if your prediction is greater pay, you should definitely belong to a pay class, right? And the other is exclusive knowledge, which means if you are predicted to be greater pay, you cannot be lesser pay anymore, right? So such thing is very interesting, and such knowledge can be easily built up by using a WordNet types of knowledge base, etc. And only based on such simple knowledge rule, which can be represented as a first order logic and embedded to MLN itself to build our sensing reasoning pipeline, as we mentioned. Very interesting, we can see under benign accuracy, it's not only like not dropped, but also improved a little bit, because we know that usually should be a trade-off between benign accuracy and robustness, right? But here, very interesting, we can see there's no trade-off because we bring in additional information, right? The benign accuracy is a little bit improved. But if we look at the certified robustness or certified rate means that with perturbation, the prediction will not change. And the certified robustness means that within certain predation, it will not only not change, but also the same with the ground truth, right? Slightly more strict. And in this way, we can see under different smoothing parameter, which just diverse of models, and different percentage of the sensors randomly can be attacked. And with knowledge, such a pipeline can dramatically improve the certified robustness compared with model without knowledge. I would say the improvement of certified robustness currently is very marginal improvement for statistical models, like even 5 or 6% is large enough. But here is around like 30% or 40%, which is quite significant, benefited by the domain knowledge, I would say. And we can see that we can achieve both high benign and certified robustness for the sensing reasoning pipeline, which I think is very promising and interesting. And with this, we now know how to certify the robustness of MLN itself, right? And second, we actually want to know whether or not indeed such knowledge integration will be provably robust than a single model, right? Before we just show it, but how tight it is and under what sufficient conditions this will be true, and when we should use such a pipeline, right? So to answer those questions, let's look at more concrete types of knowledge here. So coming back to our favorite example of the row sign classification here. So as we mentioned before, still we can take this, say, any row sign input as an input, and we can train different sensors, right? As we mentioned, there is a main sensor to predict what types of sign it is, and there are some knowledge sensors to predict the contents, the colors, the shapes, the pattern, whatever. And in particular, we'll have two types of knowledge here, similarly as before. One is we call permissive knowledge, meaning that if, say, this sensor predicts there is a stop pattern inside sign, and it indicates it must be a stop sign. So which means SI will infer the Y, which is the prediction of the main sensor, right? And on the other hand, there will be a pretentative knowledge here, which means that if you predict the sign is the row sign itself, then it indicates it must be Orton shape. It cannot be of other shape, right? So basically the sufficient and the necessary directions both. And we will use SI to represent the permissive and SJ represent the preventative knowledge. And in order to model or analyze their robustness or lower bound of such robustness of such a pipeline, first we need to understand a little bit more or use something to characterize the properties of the sensors itself, right? So very simply, we can use the truth rate and false rate to analyze the knowledge sensors. For example, we can use alpha and the epsilon. And the permissive knowledge meaning that under the main sensor prediction is 1, and the knowledge sensor prediction should the same with it, and for the preventative one, the other direction, because it's a necessary condition, right? And we will use such, remember the alpha and the epsilon here in order to characterize the properties of the sensor models or knowledge sensors, right? And in order to do, based on such a characterization, we can actually prove the convergence of such a pipeline as a function of this is a lower bound of all the alpha and the upper bound of all the epsilon. So concretely, we can see intuition here. The proof itself is quite engaging in the sense that we need to analyze the different regimes of different rule weights. And as long as you decompose different regimes and you prove under each regime and with certain Hopton bound, etc., you can achieve it. But that's technicality. And here, the most important thing is the intuition. It's very interesting that the mu here represent the contributions of different sensors. So you can see the condition is that as long as this is larger than 0, meaning that the contribution of those knowledge sensors are not 0, right? They are useful. That means as long as we use those knowledge sensors, this pipeline itself will have a lower bound of its accuracy and expressive as the how much contribution of different types of sensors, and the variance of this lower bound will be as a function of the upper lower bound of the truth rate and false rate. And you can see intuitively, if we use the lower bound of the truth rate minus the upper bound of the false rate for any sensor here, that will represent the worst case robustness of specific sensor here. Right, so that's intuition very interesting here, and concretely this shows it converge. And let's see whether or not it can be proved that indeed such a knowledge like enabled pipeline will be more robust than a single pipeline here, right? And similarly here, the intuition is more interesting, that as long as this condition satisfies this, like the pipeline, the knowledge enabled pipeline will always be more robust than main model without knowledge, right? And in order to satisfy this condition, let's look at what gamma is, right? The gamma itself can be composed by this part is just the truth rate of the main task, the main sensor, right? And this part is just what we mentioned before, the improvement by the knowledge sensor, which can be viewed as the worst case combination of the truth rate, because here is the truth rate over all possibilities of the knowledge sensor, and here is the false rate, right? This represents a margin or the worst case robustness of knowledge sensors, right? And very interesting, given such representation of gamma itself, we can see what's this condition here, right? It can be viewed as a combined truth rate of all the models normalized over the number of models. And we can see the alpha star itself, if it's 0, it means the main sensor itself is not robust at all, vice versa. So we can see that the conclusion from this intuition is that from here, if we get a larger truth rate or lower false rate, so this value will be larger, gamma will be larger, then this condition will be easier to satisfy. Then it means as long as the knowledge sensors is more robust, then this condition will be easier to satisfy, which is very intuitive, right? And the second, as we just mentioned here, if alpha equal to 0, which means the main model itself, like the neural network that we are using, is not robust at all, then this condition is very easy to satisfy because here is 0, right? And that means any improvement with knowledge and things, it will help improve the model. But on the other hand side, if the alpha here equals to 1, this thing goes to infinity large, then it means if you have a super robust model, main sensor, right, then knowledge is not useful. You cannot improve it further because it's already super robust. And with such a validation, it also verifies the tightness of such robustness proof itself, which is very nice, showing that under such a sufficient condition, which is the main model is reasonable but vulnerable, and the knowledge sensors are robust enough, then the knowledge pipeline will always be better or more robust than the single sensor here. I think this is actually given certain understanding about when we should use a knowledge sensor, and I would say the condition itself is very mild, which means usually as long as you have a vulnerable main sensor or main neural network, you can always use knowledge to improve the robustness of this main sensor itself. That's my takeaway from it. And with this proof, and the next thing is that I hope so far you are convinced that it is great that we can certify the ML reasoning component. It is also great that we can prove with knowledge. It's always helpful under very mild conditions. And now let's implement it, right? How we make it scalable, how we make it possible to realize in physical world. And the main like a challenge here is for MLN itself, for example, the inference itself is sharply complete, right? It's of high complexity, and we cannot exactly enumerate all the possible words, basically all the possible assignment of the random variables in a MLN, right? And then, of course, the question is, can we approximate it? Right, and one way to approximate it is we can use certain variational distribution to approximate the MLN, like the assignment, so that we don't need to enumerate all the possible assignment of the program itself, right? And on the other hand, after we can use a variational distribution, we need a model, need certain things to encode this variational distribution, right? And in the meantime, we also hope that such approximation can preserve the knowledge or reasoning connectivities among those sensor output, as we mentioned, right? So naturally, we think we can think of GCN, right, which exactly can encode different graph structures in GCN. Also, we know inference of GCN is very scalable. So therefore, whether or not we can leverage GCN to encode the knowledge relationship and approximate the variational distribution of MLN and make the inference itself, right? And another question is, of course, if we can do this, right, GCN has the parameters and the MLN like knowledge rules have parameter like the W we mentioned before, how we train those weights, right? How we train this end-to-end scalable pipeline, etc. So this is another important question and a very headache question, right? But after all, we can see a brief example. You can see this is possible and also very directly implementable. So first of all, let's quickly recall our sensing and reasoning component, right? So for sensing, we have main sensor. In this example, we're trying to predict this animal is a panda, is a dolphin, or is other types, right? And we have different knowledge sensors to predict whether it has flippers, is furry, is aquatic, so that you can see the knowledge. If it's panda, it should be furry, right? Etc. etc. And now, because this implemented by MLN is not scalable enough, as we mentioned, we hope to use a GCN to encode it and make the approximation of the inference of MLN, right? And concretely, we can use a variational EM algorithm, which is given this graph structure, which is implemented by the knowledge rule here, right? For example, here, this shows the panda node, this shows the dolphin node. And if it's dolphin, it should connect it with the flippers and the aquatic, and if panda is furry and clouds, etc., right? And then during the inference step, you will fix the weights of the MLN and use the GCN itself to make inference, right? So it will make the inference and estimate the posterior distribution, and therefore to make inference, right? And in the meantime, we can also, once we optimize the weights, we fix it, and then optimize the GCN weights itself to match the prediction probability here, right? Essentially, our goal can be simply viewed as under the encoded posterior distribution by the Q theta here can be viewed as GCN here, and the T here is the output of all the sensors. Under this like posterior distribution, we want to minimize the encoded posterior distribution here and the true distribution and minimize their, say, KL divergence, right? And we can optimize by training, we can optimize this elbow to optimize the parameters iteratively with this EM step. So eventually we can get the GCN trained, and then with given this, after training, we can just fix the GCN parameter, give the input of different output of the sensors to it, and make scalable inference immediately. And then that output of the GCN will be the prediction probability for all the the classes, and we can take a simple argmax and get the final prediction, right? So with this, so far, I think, or I hope you are clear that sensor reasoning great, and we can certify the robustness of it. And to make it more scalable, we can use GCN to encode its posterior distribution. And in this case, we have a fully scalable end-to-end pipeline with sensing and reasoning, right? And the next, let's look at some quick example to see what we can enable to use such a scalable sensing reasoning pipeline. What applications we can do, right? People are interested in applications, and we can see, of course, as we mentioned before, this road sign classification, we can easily encode it and do such a sensing reasoning pipeline. And against some like a word 50 classification, which trying to classify 50 words into different word categories. And then the knowledge we can use here is that if you predict this word to be, say, a dream, then we know the first position of that word should be D, right? And also on the other direction, if you have those three like characters at different positions, you can actually allocate a word itself. So these are the knowledge rules as an example that we can use. And not only against the images, right? As we can see so far, all the input and the models and the knowledge is not specific to any types of domains, right? So that's why it's possible to build up such a sensing-reasoning pipeline for NLP domain as well, for example, right? This is a simple information extraction based on NLP stock news. And basically there are sensors to predict the stock price, to predict the stock price change, etc. And the simple rules we can use is the like the common sense knowledge rules, like the arithmetic rules. For example, the price of the stock of today minus the price yesterday should equal to the stock gain prediction here, right? So basically with such simple knowledge rules, it's possible to improve the robustness of such an information extraction pipeline. And more interesting, it's also possible, as we promised, to leverage such a sensing-reasoning pipeline for specific security application, for example, PDF malware classification here, right? Basically, if you have the input as a PDF malware, which can be represented as a path trace here, and then the knowledge we can use is some malicious malware will indicate some existence of the path, and the passes itself have the hierarchy behavior. For example, if you have this path, you definitely have this path, right? Because it's child of it, etc., etc. So with all these applications, I just hope that you are convinced that it's possible to implement or develop such a sensing reasoning pipeline on different applications. And also, as you can see, so far, all the knowledge rules we discussed are common sense and intuitive to human, right? But unfortunately, current data-driven statistical models cannot even integrate those such simple knowledge rules. So therefore, such way will help to enable the capabilities of machine learning models to explicitly consider those knowledge rules during prediction and therefore improve the robustness, right? Because as you know, in security domain, the consistency and the resiliency is one fundamental principle that we can leverage to improve the safety or robustness, right? So then I will not dig into all the results. As you can see, all the results can be like certified. And if you're interested, you can take a look at the concrete result. Here, I'll just want to give one example about such a sensing reasoning pipeline in terms of the certified robustness, as we mentioned before, and similar here, compared with all the state-of-art single model certification, it will significantly improve the certified robustness, especially under large radius, which is of practical implications, right? And not only on certified robustness, which is very important, right? But also against some real-world attacks, like say we naively just use PGD attack different models, still empirically, it is also more robust. And another interesting thing you can see is that such a pipeline, as you see, it's not it's agnostic to different modalities, as we just showed, right? But also it's also agnostic to different types of attacks, because during the training and building the pipeline, we never consider what would be the potential attack we will be against with, right? So in this case, it's actually possible to evaluate such a pipeline against all the types of attack, you name it, LP bounded, white box, black box, or the etc. So basically, similar here, not only benign accuracy, not sacrificed, but also very interesting here. This x-axis show all the types of attack. This is white box, black box, and the bar shows improvement, which means under all types of attacks, the improvement is large, and there is no longer a trade-off between the benign accuracy and robustness of such a sensing reasoning pipeline, which is very nice, and also thanks to the additional information it brings in, right? And slightly more concretely, we can see that to make this more concrete, right, such an attack could include like the physical attack we mentioned before. The robustness improvement is quite significant with knowledge, right? And also all kinds of like the common and unforeseen corruptions like fraud of JPEGs, whatever types of attacks, the model itself will improve the robustness for it. And the last I will show a very interesting case study that why such sensing reasoning pipeline will improve robustness, right? So here's a simple example as we shown before, the dolphin and panda, right? There is some like attributes they have. And if we give a vanilla, give this input to a vanilla model, so this is a dolphin, this is a panda, it's correct, classified very nicely. But if we attack it, as you can imagine, the attack confidence is very high, right? The panda is misrecognized. But after the sensing reasoning pipeline, you can see because some important sensors here are not attacked. For example, some important sensors here, like swimming water, are relatively robust. You can see the model will recorrect the prediction probability. Therefore, the dolphin will still be predicted after the sensing reasoning pipeline. The main contribution is that those knowledge sensors will help. And remember our alpha minus epsilon, right? As long as some knowledge sensors are more or less robust, it will have dramatic impact and improvement. So far, not only against the prediction models, we can leverage knowledge, but also against the different like generative models, we can use knowledge, we can use causal relationship and knowledge to improve their robustness, etc. Right? So hopefully this can provide a different view for you if you want to improve or build up the robust or trustworthy machine learning models. And in the end, under different domains, some useful resources could be, we have this robustness testing against the autonomous driving to provide more than 3,000 safety critical scenarios to test it with certain knowledge for some scenarios, and some robustness certification against the testing time, training time, attacks for reinforcement learning, for NLP models, for like federated learning, etc., etc. So a lot of interesting angles. And the one main thing I want to mention is, I think with knowledge integration and the reasoning ability, it can largely improve the trustworthiness of our machine learning model pipelines. And yeah, in the end, thanks everyone. I think I will put this slide here as the last slides. Hopefully we can realize the interconnections among the different disciplines of under this big trustworthy machine learning umbrella. Yeah. Okay. Thank you, and happy to take questions.
Thank you very much for a very interesting talk, Bo. So the audience, please type in your questions in the Q&A, and then I'll ask them for you. Okay, while we're waiting for questions, I have a quick question, Bo. So this inference, have you looked at the temporal aspect of this? Because it seems like spurious things happen temporally and you can skip things very quickly, right?
Yeah, exactly. So we actually have some work before using spatial and the temporal consistency, etc., to help recognize the consistency to identify vulnerabilities and improve robustness. That's one perspective. And on the other perspective, from the sensing reasoning knowledge pipeline we discussed today, it's also possible, for example, if you want to certify the robustness of, say, reinforcement learning pipeline, they naturally have these temporal properties, and in each step they have different actions and observations. So it's possible to integrate those temporal consistency as types of knowledge and try to lower bound the action prediction, for example, under certain crafted state adversarial observations. So yeah, it's quite possible. And
very interesting. Very interesting.
Yeah.
We have a question here from Andrew. He asks, can this technology be used for the healthcare industry? Do you have any specific ideas how this could be implemented?
Oh, healthcare industry, definitely. So indeed, that's a very good question. So we do have some collaboration with some the Cleveland Clinic, like they give us some like MRI data set. So basically, the goal is to do the segmentation for tumors and things, right? But as we know, this is a standard task but very challenging. So with certain common knowledge, for example, with the expert, this all like knowledge, I fully rely on those doctors that they have good background about what types of like a thickness of the boundary should be reasonable, and if your prediction is larger than some area or overlap, it is abnormal and things, so that we can eliminate sort of either random like predictions of the segmentation, or even sometimes adversarial segmentations for those MRI data set. And I think this is very possible, and indeed is some of our ongoing work as well. And from the other perspective of NLP perspective, I know people are already doing something. I think from actually Professor Ericsson's group, who will also give a talk later, they actually have a pipeline to using adversarial attack to identify the notes of the doctors to see which word is most important for specific prediction. But this thing can be attacked, as we see, right? So we can attack some text so that the prediction of things will be misrecognized. Therefore, the domain knowledge here, as we mentioned in the NLP example, can be leveraged to predict the either like treatment procedures or identifying the importance for explanation, but in a trustworthiness way. Yeah, it's very possible.
Very interesting. In fact, the doctor notes themselves adversarial attacks in and of themselves, right?
Yeah,
So,
exactly.
Yeah, thanks very much. So we're at the end of the hour. So I'd like to thank our speaker, Dr. Lee, again for a fantastic presentation. You can reach her at her email. Thanks again very much. Okay, bye-bye.
Thank you.